Hello learners, welcome to session 1 of unit 2 in the course Introduction to Abstract Algebra. I am Munkaila Dasmani and I am a course instructor. So in this session 1 we are looking at relations on a set. In this unit we will cover relation on a set, composition of functions, equivalent relation on a set, partition of a set, partial order relation on a set, and you also look at well ordered sets. So this unit is very interesting. By the end of this session, you should be able to define Cartesian products of two sets, define a relation, also generate other sets from a given set using a relation. You should be able to determine the domain and codomain of relations. Okay, so let's look at relations on a set. Relation on a set. So if you remember, we said that a set is a well-defined collection of objects. That is, it is defined in such a way that we can determine for any given value x whether or not x belongs to the set. The objects that belong to a set are called its elements or members, and we said that sets are denoted by capital letters such as capital A, B, C, and the rest. So if small a belongs to the set capital A, let's say this small a can be a member of this big set, then the A is element of the set A. We denote that, and we talk about this where in level 100, level 200. So in this particular course, we are looking at relationship between these the relations on this set. So let's look at definition of ordered pairs. Let me clean this one. So let x and y be two sets. As usual, we say that sets are denoted by capital letters. Let x and y be the two sets. So let's consider ordered pairs xy. Ordered pairs xy. So here we say that the x is a member of the big X and then y is also a member of the big Y. So by considering this ordered pair or this set xy, so the xy is called the ordered pair. This one is called the ordered pair. The ordered pair. The ordered pair. Given these two sets. So in ordered pair, in order in which the two elements are written is very important. That is, xy is actually not always the same as yx, not always the same. They can be different. So the order of writing this are very important. So in that instance, so two ordered pairs are said to be equal if their corresponding components are equal. That is equality. For instance, when I have x1, y1 equals to x2, y2. These ordered pairs are equal if only and only if x1 equals x2 and then y1 equals y2. Then we say that these two ordered pairs are equal. If not, then here x is not equals to y because they are not equal. So the first part they are not equal, but this later they are equal. So that is what we call ordered pairs. Let's look at example in the next slide. Before the example, let's look at what a Cartesian product means. So the Cartesian products of xy, we read it as x cross y of the sets x and y in the set of all possible ordered pairs xy, where x is a member of the big X and y is a member of big Y. Now that we understood what the ordered pairs is, this means that we use the ordered pairs to find out a Cartesian product. Good. Let's look at the example. Example 1. If x equals to 2, 4, 6 and y equals to 8, 1, then we want to find x cross y. X cross y. And remember, we are saying that the members, so here all these are the members of big X and all these are members of big Y. And then their ordered pairs are not always equal. So here x cross y, you take the first x, you cross it with y, so we get 2 8, 2 8, and then 4 8, then you come and get 6 8. You take the again 2 1 2, that's 4 1, and then 6 1 in that order. So this one is the cross product of the x plus y. Also, let's look at the y plus x. Y plus x gets 82, 84, 86, and this up to 16. Now, looking at the 2, you can actually tell us as that xy actually not equals to yx. So the ordered pairs are not always equivalent. They are not equal to. Great. Apart from the set of all real numbers, other sets of numbers can be used to describe Cartesian products. So let's look at ways of describing Cartesian products. So one of them is we can use integer, that is n, the set of natural numbers, and you know that the set of natural numbers start from 1, 2 for the purpose of this study up to infinity. We can also use up to infinity. We can also use sets of integers, and that one is denoted by z, and a set of integers, you know, that it can both negative, let's say -2, -1, 0, 1, 2, that's all that. So that's the set of integers. You can also talk about set of rational numbers, and I know you know rational numbers. If you forget about them, please go and find them, read them, because we'll be using them. Rational numbers, and we can say that p, q, you know, rational numbers can be written as this common fraction p and q, where p and q are all integers. And q is not equal to 0. Q is not equal to 0. Once q is equal to 0, we say that it is undefined. Then we can also talk about complex numbers by c, denoted by c. Complex numbers. So complex numbers, and that one too, we write it as a plus bi, where both a and b are members of R. They are all real numbers, and that is a complex number. Note that I is actually equal to square root of -1. So square root of -1 gets I in the complex number sense. Okay. So apart from the set of real numbers, these are what we can use to describe Cartesian product in this course or in this model. Now let's look at what a Cartesian product actually is. What is a Cartesian product actually is? So a Cartesian product is a relation. So a relation is any arbitrary subset of Cartesian products between two sets x and y. So that for relation R, that's real numbers, R is a subset, it's a proper subset of x cross y. If the ordered pair x and y is an element of R, where x is a member of the big X, and then y is a member of the big Y, then we say that x is related to y by R. X is related to y by R. So we learn how to write that x relates to y. So normally write it like this: x is related to y by R. So we're learning this one, how to write a relation, in the subsequent session. Good. So that is the Cartesian product. So example, if n is the set of natural numbers and R is the relation, what is relation? It's a multiple of. Okay. So let's see, if 18 2 is a member of R, 18 Is a member of R? Is a multiple of. Because 8 is a multiple of 2, then we can say that 18 is a member of R. And the reason is that 18 is a multiple of 2. So multiple of 2 get 18. For that relation, what about 24 and 5? 24 and 5 is a multiple of. So let's see which number when you multiply, or 5 multiples, which one will give 24? You get 20 and 25, but you don't get 24. Then we say that it's not a member of R. It's not a member of R. 24, 5, the ordered pair 24, 5 is not a member of R. So here we can say that R belongs to a natural number. Good. Example 4. If Q is the set of all rational numbers and R is the relation, is greater than, then what can we say about 3, 2? 3, 2. We can clearly say that 3, 2 is a member of R. The reason is that 3 is greater than 2. It's greater than. So 3, 2 is a member of R. What about when I write 10, 20? Can you say it's a member of R? Certainly no, it's not a member. 10 is not greater than 20. So assignment, find out minus 10 and then minus 2. Is minus 10 greater than minus 2? Example 15. Let n be the set of all natural numbers and R the relation. So we have the relation here, a and a squared are all members of where a is a member of n. So a is a member of natural number. So this has been done. So we want to see 2 and so 2 and 8 is a member of R. Is it true? And the relation is what? A and then a squared. A squared. So let's see if a and a squared. So 2 is 2 the same as 2 squared. So get 8 equals to 2 equals to 8. Is it true? And that is actually not true. It's not true. And the reason is that 8 is so 2 and then 2 squared. I get 2 and 4. So 4 is not equal to 8. So in that instance, we say that 8 is not a member of R. It's not a member of R. It's not a member of R. So it's not. And then we look at II, 4, 16. So you know that 4 and then 4 squared is the same as 4 and then 16. In this instant, we say that, say whether or not the following are true or false. So it's a member of R. So we can say that this is true. So this one is true. The first one is false. And the last one, 9, 3. So let's see. So 9, 3. So is 9 squared the same as 3? No. So this one is false. So the first one is false, the second is true, and the third is false. And that is the relation. Okay, functions. Let's look at functions. We will define a mapping of function f being a member of x cross y from a set x to a set y to be the special type of relation in which for each element x be a member of the big X, there's a unique element y also a member of the big Y, such that this condition hold. And why the condition? The ordered pair x, y are members of f. Good. So that's how we are going to define mapping here. So in this case, x is referred to as the domain of the function and y is also referred to as its codomain. Elements in the codomain, which are images of the elements in the domain, constitute the range of this function. And I remember unit 1 we dealt with that. So don't forget about your injective mapping. surjective mapping and bijective mapping. If forgotten about them, please go and revise them. And then if you want, you can also find more example in your course material here. So alternatively, for every element in X, F assigns a unique element in Y, and that is X, Y are all members of F, where X is a member of the big X and then Y is a member of big Y. So that's another way we can say for every element in X, small x, F assigns a unique element in Y, and that is functions from the cross product perspective or the ordered pairs. Great. Let's look at this example. Which of the following or which of the relation is a mapping or is a function? The first one a function, that is F. We have F and G, so F is here and then G is here. So which of the two is or a function, or you can say a mapping? So let's see the first one. So you can actually say that F is actually a function, but G is not. And what is the reason? For each element in X, there is a unique value. It assigns a unique value. So F of A equals 2, F of B equals 2, F of C equals 4. Remember, we did something like this, and then for G of A equals 1, another G of A equals 3. Look at this coincidence. Then you can say G of B equals 1, and then G of C equals 4. So what is making G not a function is because of this. So which one? You are saying G of A is 1. At the same time, you are saying G of A is 3. So which is which? And because it contradicts itself, and that makes it false. So G is not a function. Find more examples in your course material, because there are a lot of examples there.